Hello everyone. Today we're taking a break from discussions about 13P Atlas and turning our attention back home, our own planet, Earth. Can we actually make it through a video without mentioning the interstellar comet? Let's try. Today's topic is absolutely fascinating. Researchers have discovered a massive gravitational anomaly deep within the Earth, stretching for thousands of kilometers near Africa. What could possibly cause such a phenomenon? Let's dive into this extraordinary geophysical mystery. There's a curious paradox in modern planetary science. We know more about the surface of Mars than we do about the deep interior of our own planet. We send probes to explore distant moons of Saturn, land rovers on asteroids hundreds of millions of kilometers away, yet the center of the Earth remains fundamentally inaccessible to direct exploration. Why is that? The answer is simple but daunting. Conditions deep within the Earth are utterly extreme. Pressure in the outer core, about 3,000 kilometers beneath our feet, reaches roughly 1.3 million atmospheres. Temperatures there are estimated to be around 4,000 to 5,000 degrees Celsius, rivaling the surface of the Sun. No known material could survive intact under such conditions. Even the strongest steel would behave like warm butter. Diamonds would vaporize. The deepest hole ever drilled by humanity, the Kola super-deep borehole in Russia, reached only 12 kilometers, less than 0.2% of Earth's radius. And even at this relatively shallow depth, temperatures already exceeded the limits of drilling equipment. So how do we study the planet's interior if we cannot access it directly? The answer lies in indirect methods, geophysical techniques that allow us to see through solid rock using measurable physical properties at the surface. Geophysics is essentially the art of making inferences about invisible structures using careful measurements of physical fields. It's like medical tomography, but on a planetary scale. Different methods provide complementary insights into Earth's interior. Seismology, the study of seismic waves generated by earthquakes, is perhaps the most powerful of these techniques. When an earthquake occurs, it generates waves that propagate through the entire volume of the planet. These waves travel at speeds that depend on the density and elastic properties of the materials they traverse. By carefully measuring how seismic waves behave, their velocities, propagation paths, reflections, and refractions, seismologists can construct detailed three-dimensional models of the Earth's internal structure. Geomagnetism studies the Earth's magnetic field, which is generated by electric currents in the liquid iron of the outer core. Variations in the magnetic field over time and space provide clues about dynamic processes occurring thousands of kilometers beneath the surface. Then there is gravimetry, the precise measurement of Earth's gravitational field, which is the focus of today's story. Gravity at any point on Earth's surface depends on the distribution of mass beneath that point. Measuring variations in gravity allows us to infer differences in the density of subsurface rocks. We all learn in school that the acceleration due to gravity at Earth's surface is 9.8 meters per second squared. This is a convenient value for introductory physics calculations, but it's only an approximation. Gravity actually varies significantly from point to point across the Earth's surface. Why does this happen? Several reasons. First, the Earth isn't a perfect sphere. It's flattened at the poles due to its rotation, forming an oblate shape. Gravity is slightly stronger at the poles than at the equator, simply because you are closer to the planet's center of mass. Second, topography matters. If you're standing atop a mountain, there is less mass beneath you than at sea level, so gravity is slightly weaker. Mountains are essentially excesses of mass above the average surface. Third, and this is the crucial point, the density of subsurface rocks varies. If there's a dense granite body buried kilometers underground, the gravitational pull at that location will be slightly stronger. Conversely, a cave filled with air or a sedimentary basin with lower density rocks will produce slightly weaker gravity. These variations are small, typically measured in milligals, where 1 gal equals 1 cm², but modern instruments called gravimeters can measure gravitational differences with extraordinary precision. Move a gravimeter just a few meters horizontally or vertically, and you can detect measurable changes in gravity. This sensitivity makes gravimetry extremely valuable for practical applications. The mining industry relies heavily on gravimetric surveys. Metal ores, particularly deposits of iron, nickel, and copper, are significantly denser than the surrounding host rocks. They create positive gravitational anomalies, regions where gravity is measurably stronger than expected. Exploration companies fly aircraft equipped with highly sensitive gravimeters over areas of interest, mapping subtle variations in gravity. These airborne measurements can highlight promising targets for further investigation, locations where gravitational anomalies suggest substantial mineral bodies buried beneath the surface. The oil and gas industry also uses gravimetry in a complementary way. Sedimentary basins, depressions filled with thick sequences of relatively light sedimentary rocks, produce negative gravitational anomalies. Mapping these basins is crucial for hydrocarbon exploration, since oil and natural gas predominantly accumulate in sedimentary rocks. Gravimetry has additional applications in geotechnical engineering, hydrology, locating aquifers, archaeology, detecting buried structures, and even active volcano monitoring. Changes in gravity over time can indicate subsurface magma movement, providing early warning signs of potential eruptions. While terrestrial and airborne gravimeters are invaluable for local and regional studies, mapping Earth's gravitational field on a global scale requires a different approach: satellites. In 2002, NASA, in collaboration with the German Aerospace Center, DLR, launched the GRACE mission, Gravity Recovery and Climate Experiment. GRACE was ingeniously designed. It consisted of two identical satellites flying in formation, separated by roughly 220 kilometers, orbiting the Earth at an altitude of about 500 kilometers. As the satellites traveled around the planet, the precise distance between them was continuously measured using microwaves. When the lead satellite passed over a region with slightly stronger gravity, indicating an excess of mass below, it was subtly accelerated, momentarily increasing the distance between the two satellites. The trailing satellite experienced the same acceleration as it approached the same region. By meticulously measuring these minute variations in separation, scientists could calculate variations in Earth's gravitational field with unprecedented precision. The GRACE mission operated from 2002 to 2017, 15 years of operation, far exceeding its originally planned lifespan. During this period, it revolutionized our understanding not only of Earth's internal structure, but also of dynamic processes such as glacial melt, groundwater depletion, and ocean mass movement. In 2018, a successor mission called GRACE Follow-On was launched, continuing this critical work. Between 2006 and 2008, while analyzing GRACE data, researchers identified something extraordinary: a massive gravitational anomaly in the Atlantic Ocean near the coast of Africa. This was not a minor local variation. It extended approximately 7,000 kilometers, truly a continental-scale feature. The magnitude of the anomaly was equally striking. The strength of the gravitational signal simply did not match any superficial explanation. Could it be variations in ocean depth? No. The seafloor topography was well mapped and could not account for the signal. Could differences in seawater temperature affecting density explain it? Calculations showed that an absolutely unrealistic volume of water, arranged in an impossible configuration, would be required to produce such an anomaly. It became clear that the source of this massive gravitational anomaly was not at or near the surface. It lay deep, very deep, within the Earth. But just how deep, and what could generate such a continental-scale disturbance in the planet's gravitational field? Through sophisticated geophysical modeling, combining GRACE gravitational data with seismological information and other geophysical constraints, researchers traced the source of the anomaly to a surprising depth, approximately 3,000 kilometers below the surface. To put this depth in context, the Earth's radius is about 6,371 kilometers. 3,000 kilometers places us near the boundary between the mantle and the outer core, one of the most fundamental interfaces in planetary interiors. The mantle is a thick layer of solid rock, though capable of flowing very slowly over geological timescales, that extends from the base of the crust to roughly 2,900 kilometers deep. Beneath it lies the outer core, composed primarily of liquid iron under extreme temperatures and pressures. This mantle core boundary represents a dramatic discontinuity in composition, density, and physical properties. It is precisely in this deep region, near this critical interface, that researchers identified the source of the massive gravitational anomaly, a sudden and substantial change in the density of the material. What could cause such a dramatic density change at these extreme depths? The most likely explanation involves something called a mineral phase transition, a fascinating phenomenon in materials physics under extreme conditions. Minerals, ordered crystalline arrangements of atoms, can exist in different crystal structures depending on temperature and pressure. The same chemical composition can form structures with dramatically different densities. A familiar example is carbon. At normal surface conditions, carbon forms graphite, a relatively open structure with a density of about 2.2 GeCeCO3. Under extremely high pressures, the same chemical composition forms diamond, a much more compact structure with a density of 3.5 GeCeCO3. The graphite to diamond transition is a pressure-induced phase change. In the deep mantle, silicate minerals undergo similar phase transitions. At depths of hundreds to thousands of kilometers, increasing pressures force atoms into progressively denser crystal structures. Each transition results in a sudden increase in density, sometimes 10% or more. The specific phase transition responsible for the Atlantic Gravitational Anomaly likely involves silicates, transforming into ultra-dense crystal structures characteristic of conditions near the mantle core boundary. The associated density increase, concentrated over a region thousands of kilometers wide, creates the powerful gravitational signal detected by GRACE. But what triggered this phase transition in the first place? Mineral phase transitions don't occur spontaneously. They require some perturbation in local conditions. The most likely explanation involves vertical movements of mantle material. The Earth's mantle, though solid on human timescales, flows slowly over geological time through a process called mantle convection. Hotter, slightly less dense material rises from depth, while cooler, denser material sinks. This convective movement, driven by the gradual release of primordial heat from Earth's interior, is the fundamental engine of plate tectonics and nearly all surface geological activity. When mantle material moves vertically, whether rising or sinking, it experiences dramatic changes in pressure. These pressure changes can push the material across phase transition boundaries, triggering sudden structural transformations and corresponding jumps in density. The Atlantic Gravitational Anomaly likely marks a region where vigorous convective motion in the lower mantle is driving material through significant phase transitions. This discovery does not exist in isolation. It connects to other mysterious geophysical phenomena that researchers have been studying. For example, seismological studies have identified ultra-low velocity zones near the core mantle boundary, regions where seismic waves propagate inexplicably slower than expected. These low-velocity zones are thought to represent material with unusual physical properties, perhaps partially molten or with an exotic chemical composition. The Atlantic Gravitational Anomaly may be related to these anomalous seismic structures, both reflecting the complex dynamics of the deep mantle. There are also potential connections to Earth's magnetic field. The liquid outer core, just beneath the region where the gravitational anomaly is located, is where the geodynamo operates, generating the magnetic field through electric currents in convecting liquid iron. Processes occurring at the core mantle boundary could influence flow patterns in the outer core, potentially affecting the magnetic field. This discovery fundamentally challenges old conceptions of Earth's lower mantle. Historically, geophysicists tended to imagine the deep mantle as relatively static and uniform, a passive transition zone between the geologically active upper mantle and the fluid core below. The massive gravitational anomaly dramatically demonstrates that this picture is incorrect. The deep mantle is dynamic, active, and structurally heterogeneous. Significant density changes can occur on geologically rapid timescales, perhaps millions of years, or possibly even faster. This revelation has profound implications. If the deep mantle is as dynamic as it now appears, processes there could influence surface phenomena in ways we do not yet fully appreciate. Volcanism, earthquakes, and even long-term climate variations through variable heat release from the interior, all could be connected to the deep mantle's dynamics. It is humbling to recognize just how little we still know about our own planet. We live on the thin, fragile surface of a massive rocky sphere with an interior that remains largely unexplored and only partially understood. Discoveries like the Atlantic Gravitational Anomaly remind us that profound mysteries are not billions of light years away, but literally beneath our feet. The more we learn about Earth's interior, the more complex and fascinating it becomes. If such dramatic changes can occur in the deep mantle, what other surprises await discovery? The next generation of geophysical missions, more sensitive gravity satellites, expanded seismic networks, and increasingly sophisticated computational models will undoubtedly reveal even more mysteries. Today we took a break from 13P Atlas to explore the geophysical wonders of our own Earth, proving that we do not need to look to interstellar space to find extraordinary phenomena. Our home planet still holds spectacular secrets waiting to be uncovered.